different images or two different arguments always have two different images, and there is at least one pre-image for all image from the set B, right? Okay, so that was the case. So that's why the elements were of equal size, so because there exists a bijection between the two. And here we extend this definition, so since there exists a bijection between a set of natural numbers and a set of integers, then this means that there are just as many integers as natural numbers, which means that both sets are countable. Okay, so this means that this implies that Z is also countable. All right. Okay, so the cardinality of the set is not larger than that of the natural numbers. See what I'm saying? Okay? This is very important that you understand this, guys. And this is very weird, right? Because, you know, okay, so then actually you would have, you know, the set of natural numbers, which is a strict subset of the set of integers. All right? So there are, in both sets, there are just as many elements as in the other. So in the two sets, all right? So if, let's say if you have the integers and you take out all the natural numbers, then what's left is actually just as large as the set before, okay? So just because you take out something, it doesn't mean that it's getting less, right? In mathematics, that works. That's how it is, right? I think it's a weird concept, guys, you know, so most people don't understand this at all, right? And I understand that basically, so I comprehend what the problem is, because you have a strict subset and then you take, you know, things out, and actually what you have is just as large as the set before, so it doesn't change anything, but this is how it is, okay? So in case, let's say, for infinity, there are new rules that apply, so that's a problem, okay?
What does the zero of LF refer to?
That just, you know, this refers to the smallest cardinal number, okay, which is greater than that of any natural number, okay? Because we will see that here, for instance, and this is going to be the case. Now, I would like you to also to show you the countability of the set of rational numbers. So if you add, let's say, the set of rational numbers, you know what the set of rational number is, okay? But maybe you can denote this, that a set is countable if and only if it can be written as a sequence. Okay, so this is going to be a remark. A set is countable if and only if it can be written as a sequence. Why is that? Because actually a sequence of non-repetitive repetitive numbers, because a sequence is actually nothing but a bijection, or let's say a function from the set of natural numbers to the set of, let's say, another set that we actually imagine. Okay? All right. So for instance, let's say you would define, I mean, let me just give you actually a definition. So you know what a sequence is, right? So for instance, for the Fibonacci sequence or whatever, okay? Okay, so a sequence is actually a function that goes from the set of natural numbers to, let's say, the abstract set omega, on which the sequence is defined. Okay? Okay, so then a n is called a sequence. Okay? On omega. Okay? Actually, you know what a sequence is, all right? So for instance, whatever, I mean, just give you an example, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so forth, right? Okay, so that could be, for instance, the first element, that could be the second one, that could be the third one, right? And so forth, okay? So we have that we assign for a natural number, we assign a certain element from the abstract set, and that is generating a sequence. Now, a function is bijective, so the function is countable, or a set is countable, let's say, if and only if it can be written as a sequence, because if it can be written as a sequence, then there is a possibility, actually, that the set, or the function on which it's actually the sequence is defined as actually bijective. Okay, so let me just give you an example. For instance, the set of rational numbers. Okay. All right. So here in that case, for instance, the set of rational numbers. Numbers q, okay, is countable. That means that actually even the set of rational numbers is not getting larger as the set of natural numbers. So there are just as many fractions, positive and negative, as natural number guys. This is also, very, very strange. But I would like to show you that this is countable. So the set of rational numbers is countable. And let me just demonstrate how you would calculate the set, or how you would count actually the set of rational numbers. Now it's sufficient actually, guys, to focus on positive rational numbers. So rational numbers are numbers that can be written as fractions. You know that, right? So for instance, let's start with 0, okay? Then I continue with 1, okay? So what I'm doing is I'm preparing to 1, 2, 3, 4, etc., etc. So here in the next line you would have also 1, 1 over 2, 1 over 3, 1 over 4. Okay. Okay, so here you would have 2 over 2, which is equal to actually to 1. So here in this case, no, let me just start with that. So here in this case you would have 2 over 2. No. Guys, I really apologize. I don't know what happened to me, but last night or something, whatever. So this is caffeine, so do not stop drinking coffee. Okay. Anyway, just let me just add this here. So these are 1. Okay. So no. Okay. I apologize. These are the wrong numbers that I would set up here. It's my fault. I apologize. So here, okay. So 1, 2. So here would have, let's say, 1 over 2. Okay. I hope it goes away by the end of this week. So here you had 2 over 2. Okay, now this is it. Okay, so 3 over 2, 4 over 2. Okay, that goes on. So actually the denominator is 2. So here in the next section you would have that denominator is 3. Alright, so here 1 over 3, 2 over 3, 3 over 3, 4 over 3, etc., etc. Okay? And here you would have actually then 1 over 4, 2 over 4, 3 over 4, and so forth. Okay? So you would find actually you would have all positive fractions here, including 0. And that means that if you have the positive ones, then you can add the negative ones. Just we add this actually for the set of integers. So you can say 1, negative 1. Then if the next is going to be 2, then it's going to be 2, negative 2, and so forth. Okay? So we can construct a sequence where actually we would have all natural number, all fractions here. So the first member would be 0, the second one would be 1, the third member of the sequence would be 2, okay? And then we kind of construct a snake here. So the fourth member would be 1 over 2, okay? So then we go down, 1 over 3, then we go up again here, right? So there is a snake. You see this? Okay, so then we go to the right. And we go back down here. You see? Okay? So then from 1 over 4 we go to 2 over 4, which is already there. So, and then the snake evolves in such a way as a sequence evolves. You understand? Okay, so that's how you would actually generate a sequence. Okay, so let me be more precise here. So then you would, how you would proceed. Okay, so the first member of the sequence A1 would be 0, right? Okay, the second member would be 1. Okay, the third member we would take the negatives. Okay, so we would have negative 1, right? Because we need the negatives too, right? The fourth member, okay, as you can see this here, is 2, right? So we go from 1 to 2, you understand? Okay. Then we go from 2 to 1.5. Okay, so that's the fifth member of the sequence, 1 over 2. Okay? Alright? Then the sixth member is, no, I forgot the negative ones again. Sorry. Okay, so I forgot negative 2 here, so I have to include it there. Okay, so the sixth member will be 1 over 2. The seventh member will be negative 1 over 2, and so forth. The eighth member would be 1 over 3, you understand? The ninth member would be, actually you can see this here, negative 1 over 3, and so forth. So as the snake evolves, you can take actually any member of the sequence that you like. So that is actually the proof that the set of rational numbers is countable. Okay, so the cardinality of Q here is also equal to that of the natural numbers. You understand? Okay? So there are no more fractions than natural numbers, guys. Because there is a bijection between the natural numbers and the fractions. Okay? You understand this? Okay, so the set is not getting larger in terms of cardinality. Okay? Alright? Is this something that you comprehend somehow? So if the set is countable, or if it can be written as a sequence, then it's countable, which means that the cardinality of the set is not larger than that of the natural numbers. Okay? So here are actually the natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., etc. Alright? And we assign to each natural number, we assign a fraction. Okay? And this function, guys, this function, and so forth, right? So we don't stop there, but I did because I don't have more space. But this function is a bijection, okay? Because two different natural numbers always have two different images, and there is at least one pre-image for any fraction here, okay? So as maybe I could develop this as soon as I could develop a certain equation. I mean, this is implicitly given by the snake here. So if you tell me which fraction you need, then I would tell you the index of the sequence at which actually the fraction is. Okay? So that means that I could tell you where the pre-image is. So the function is surjective, which means that there is a bijection between the set of natural numbers and the set of rational numbers. So the set of rational numbers is just as large in terms of cardinality, is just as large as the set of natural numbers. Okay? Alright? New things are coming, right? So these are new concepts, right? That only very, very few people understand, so I hope you are one of them. Okay? Alright? Okay, so I told you before, you're going to learn new things that are completely contradicting to all things that you were aware of. Okay, so okay? Alright? So the set of natural numbers and the set of rational numbers are of equal size. Okay? Now, another weird concept is, and then this is another example, I'm going to add this here. For instance, okay, so let me just give you another example. So suppose we define a function. We define a function from the, let's say, from the set of open interval 0 and 1 to the set of real numbers. Okay? And it looks like this. Okay, so we have, for instance, here, this is the coordinate system. Okay? So suppose here is 1. Okay? There is an orthogonal asymptote, and I will define the function here, for instance, as follows. Okay? Maybe you've seen this before. Alright? Now guys, this function is bijective. Why is that? Okay? So F is bijective. Why is that? This is obvious. First off, two different arguments. Okay, so the arguments are here, all right, and the images are there. Okay, so two different arguments always have two different images. Okay, I would like to show you this here. So for instance, let's take that. This is A and this is B. All right. Okay. So in this case, you would see that the image of A is here on this axis, right? You see, and the image of B is here. Okay. And they are not equal. And that is also true for arbitrary points. So the function is injective. And guys, the function is bijective. Why is that? Because here you would have the set of, actually the set of all possible images. Okay, so this is the set of real numbers on which actually the function is, to which the function is mapped to. Okay, so this is a set of real numbers, you see? Okay, that is mapped to this terminal axis here, you see? And there is always a preimage no matter what. So no matter what kind of element you take here out, there is always a preimage of that regarding here. It's something between 0 and 1. Okay, so here is 0, here is 1. Okay, from this interval. Now that means what? That means that the cardinality of this interval of real numbers between 0 and 1, okay, is just as large as the cardinality of the set of real numbers in total. Okay? This means, guys, that there are just as many real numbers between 0 and 1 than between minus and plus infinity. You get that? Although this interval is a strict subset of the set of real numbers, which means that because their difference is not empty. You understand? Okay? So there are just as many real numbers between 0 and 1 as between minus and plus infinity. Okay? You might not comprehend this, right? As I told you before, we turn the world around, so this is what we do. Okay? So there are, let me write it down, so there are just as many real numbers between 0 and 1 as between minus and plus infinity. All right. Okay. Now, guys, I would like to stop here because I have to go to another campus, and I apologize for being that, that bad or something. I mean, this happened. All right. I hope this goes away. So, what I decided to do is I have to go through that. All right. Okay. Now we're going to continue from here on Friday, and please send me your assignments. Okay. Assignment 1 is published, you submit, right? Okay. So please send it if you haven't so far. Thanks.